finding the mass moment of inertia of an object is not always an easy task. Following that procedure, calculating that integral can be very complicated and can be something difficult to do when it comes to complicated rigid bodies. So one of the things that can help us to find the mass moment of inertia for complicated objects or rigid bodies is parallel axis theorem. Now, what does this theorem do is that it helps us to determine the moment of inertia of a composite object or complicated rigid body as long as we know the moment of inertia of the parts forming that composite object or forming that complicated rigid body. Now, the core of this theorem is the relationship that we can form between the mass moment of inertia about a given axis that we know, right, and the mass moment of inertia about another axis parallel to the first axis that we don't know. As long as we know the mass of the object or rigid body and the distance between these two parallel axes, we can find the mass moment of inertia about one of them, knowing the mass moment of inertia about the other one. So if I want to write it, I'll write it this way. So mass moment of inertia of a rigid body around some axis O that I don't know, let's say I'm looking for, is equal to the mass moment of inertia about an axis parallel to axis O plus mass of the object times the distance squared, the distance between those two parallel axes. So let me put them all here. This I'll define as mass moment of inertia about some axis O. Just some axis. Now this I would be the mass moment of inertia about an axis parallel to axis O. Right? So that would be the mass moment of inertia about an axis about an axis parallel to axis O, and this one is the mass of the object, is mass of the object or mass of the rigid body, mass of the object. I'm using object and rigid body interchangeably when I talk about rigid body motion, but pretty much I'm talking about the same thing. And D is the distance between these two parallel axes. Right? Distance between these two axes, between let's just say two axes. So as long as I know the mass moment of inertia about one axis and I know the mass and the distance between two axes, I can find the mass moment of inertia about the other axis. This is the core of the theorem. Now the theorem itself, the way we can apply this when we are dealing with a composite object, there are three steps we follow. First, well, we divide that composite object into parts whose moments of inertia we can easily determine. Right? So that's the first step. Divide the composite object into simple objects that you can actually calculate their mass moment of inertia. Then determine the moment of inertia of each part. Once you divide it into parts, second step, you determine the moment of inertia of each part. The third step, you just sum up those moment of inertias that you found for each part. Sum them up, and the moment of inertia you get is the moment of inertia for the composite object. Obviously, if there is the case is that there is a hole or a cutout, you have to subtract the part that is a cutout or is a hole. but the idea is the same. So you just sum up those moment of inertias that you found for each part. So following these three steps, divide into parts that you can find the moment of inertias for them, determine the moment of inertias for those simple parts, and then sum them up or subtract them depending on the type of the object and rigid body you're dealing with, and whether those parts that you are signing are cut out in holes or just another rigid part in that composite object. Now, next I'm going to take a look at a simple example, see how does this theorem work and how can we use it to calculate the mass moment of inertia for a composite object.